We should start now.
Okay.
Okay. Welcome everyone to Everrace's fifth guest lecture. This is Professor Scott Sheffield, and I'll let him take it away.
All right. So everyone can see my slides. Just shout out yes, or I don't know.
I think you can't see chat at the same time, so.
So can you see where it says Martingales and the optional stopping theorem?
Yeah.
You can't see that?
Yeah, people can, yeah. If people have questions, please, put the questions in the chat and I'll read them aloud for you. If you can answer questions, everybody. Okay,
but you can see the screen.
Oh yeah, we can see the screen.
Oh, I see. They're not able to talk.
Yeah, so what they do is they would type stuff up in the chat.
They send it to you and then you forward it on.
Then,
okay.
Yeah.
Okay. All right. Good. Fair enough. So, okay. So today I'm discussing Martingales and the optional stopping theorem. And this lecture will be very similar to a lecture that I give at MIT in my probability class, 18600. Maybe some of you will end up coming to MIT and you'll see me give something similar there. And I want to start with a problem loosely paraphrased from an MIT final exam. And the question is as follows. Imagine 23 candidates are running for a political office, and there is an efficient betting market, and P sub I represents the market percentage probability that the ith candidate wins. Okay, I want to assume that every PI is an integer greater than 1, and that the sum of the PIs is 100. Okay, so just to give you a sense of what this might look like, we can go back and look at, these are currently the betting market odds for who will be chosen to be the Democratic vice presidential nominee in 2020. So nobody knows, it all depends on what's going on in Joe Biden's mind, but people like to guess and speculate, and they have these markets where people bet. And so right now, the market seems to suggest that there's a 37% chance that Kamala Harris will win. Okay, what that means is that the last time this was traded, somebody was willing to pay 37 cents for a contract that would return $1 if Kamala Harris wins. Somebody else took the other side and was willing to spend 63 cents for a contract that would give $1 if Kamala Harris loses. So they both put in their money. Someone puts in 37, someone puts in 63, and the dollar sits there until either she wins or she loses, and then it's returned to the appropriate person. So this would also suggest that Susan Rice, in some sense, you might say has a 31% chance, Tammy Duckworth a 12% chance, and so on. Okay, so these are all the various people who the betting market thinks have a reasonable chance to be the vice presidential nominee. Now, one thing you'll know is that this market is not necessarily perfectly efficient. One thing, there are some fees involved when you play this game. You have to pay a little bit when to the site each time you make a bet and win something, and because you sort of, and in efficiency, there's usually some gap between the spread and the ask. So here it's like 63 or 62, means I can buy it for 67, or I can basically, well, somehow I think that I can buy this for 37, or I see, let me put it this way. I can buy, well, so I can buy this no for 62, or yes, maybe I can buy no for 63 or yes for 38, something like that. So anyhow, there's a gap between the ask and the spread. So so now if you go back here, what I want to imagine is that you have a market like this, 23 candidates running, and PI represents the market percentage probability the ith candidate wins, and so they all are integers. They add up to 100. I assume that the pi involve in time. So I write p sub I of t for the value at time t. And I want to assume further that if pi is a number, k, say something between 1 and 99, then at some given time, the next integer value that pi obtains is k plus 1 with probability a half and k minus 1 with probability a half. Okay, now this assumption isn't completely out of nowhere. The basic idea is that, imagine you pretend that you could actually buy or sell at the current price. Maybe it's 37 or something. And I ask you, okay, now currently I could buy or sell for 37. What's going to be the next price? Will it be 38 or 36? And if it's a continuous market, it'll be either one or the other. So imagine we know it's going to be 38 or 36. What's the probability it's going to go up to 38 first? Well, the idea is that if you knew that there was an 80% chance it would go up to 38 and only a 20% chance it would go to 36, then there's something you could do. You could say, okay, I'm going to buy at 37. Then if it goes up to 38, I sell. I make money. I make $1. If it goes down to 36, then I will also sell. But in that case, I lose $1. Okay, but because going up is more likely than going down, I'm making money on average in expectation. And so the story is that whenever the probability is not exactly 50-50, you can make money in expectation. Now, the thinking is that it shouldn't be super easy in financial markets to make money in expectation. Somehow, if everybody knew that there was an 80% chance it was going to go up to 38, people would start bidding it up the price right now instead of waiting. So somehow there's what they call the efficient market hypothesis, is also sometimes called the sort of no free money lying around hypothesis, which suggests that there shouldn't be a really easy way to make money, without or in expectation. That's one way of saying it. At least there's some caveats to this, but that's sort of the rough idea. Okay, so now, so based on that assumption of there not being any free opportunities to make money in expectation lying around, I'm going to assume that it's always 50-50 whether you go up or down. Okay, this doesn't tell you, by the way, which numbers will change in what order. I mean, it tells you if one person goes up, some other person must be going down at the same time. Otherwise, the numbers couldn't stay adding up to 100. But it doesn't really tell you how it will happen, whether one number will fluctuate a lot as news of that individual is coming out, and then another number will fluctuate at another time, or whether they will all fluctuate kind of simultaneously. But it just tells you at least what will happen for any particular person. There's always an even odds that they'll go up before they go down. Okay, so now I declare that the ith candidate makes what I call an epic comeback if p sub I gets all the way down to 1 at some point before subsequently rising all the way up to 100. We say the ith candidate is all but written off before somehow gloriously returning to win. Okay, and the question is, what is the probability that somebody will make an epic comeback before the election over? So the person who wins is somebody who got all the way down to a 1% chance, and then somehow, miraculously, they came back and won. Okay, to show you this isn't as crazy as it sounds, let me look here at this picture here. Does anyone recognize this? Okay, you can't talk, so I can't hear you. But maybe some of you recognize this as the graph of the win probability according to some computational algorithm for the 2017 Super Bowl. And this is the probability that the New England Patriots are going to win. So this was a very famous game. And so this wasn't a betting market, but it was an algorithm that tries to estimate the probability. There are also betting markets that do something similar. And they probably went up. They were doing better in the first half, so went down. They did terribly. And by halftime, they were way behind. And it looked like they really didn't have much chance. And as things went on, they went even worse, even further behind. And at one point, they were, I think it was 28-9 entering the fourth quarter. Okay, so if you know anything about football, you know that down here, the odds were getting to be well below 1%, even, you know, a fraction of a percent. So it got down to be extremely low. But then somehow, Tom Brady had this miraculous streak of good fortune. He started completing great passes, getting these runs, and somehow he managed to come back and win the game 34-28 after having been entirely written off. Okay, so this is what we call a truly epic comeback. You get down to 1% chance, and then somehow you come back to win. So the question I'm asking you is, how common are these epic comebacks? You know, would you expect to see this like every year, or once in a century, or once in a millennia? Is this something that almost never happens, or is it, you know, what do you think? At least when I frame it in the way I have it posed here, there's actually a math problem. I told you that at the beginning, you have 23 candidates. I have some set of numbers for the probability each one of them wins. And I just want to know that the probability is that one of them will make an epic comeback. So one of them gets all the way down to 1 and then makes it back. Okay. By the way, let's see if I can look here at this, at a chart down at the bottom. So they have these charts. Let me see if I can show you the longer term version. Here's over 90 days. You can see what's been happening in the betting markets. Kamala Harris went up for a while, and then she went down, and then up a little bit. Rice has been gaining. Duckworth has also been gaining. You look at these others here. There's Demings, Warren. Bass. Okay, so Warren, this is our Massachusetts senator. So, you know, if you believe Massachusetts pulled through with the Patriots, maybe we'll pull through with our senator too. So we'll have an epic comeback. Elizabeth Warren, she's currently at 7%. It's conceivable that she could somehow get down to 1% and then eventually miraculously make it all the way up. Okay, so what's the chance of that happening? Now, when these represent candidates in an election like a primary, what you often have happen is that there are polls going on a regular basis. And every time a poll comes out, these probabilities jump up and down in response to that poll. And you have candidates making comments, and then on election night itself, you have information being released out, and there's suddenly a very fast movement, things coming back and forth. But by the time you get to the end of the day, it's always the case that one of them gets all the way up to 100, the person who's won, and the others all end up down at 0. So that always happens by the end. Okay, so I would stop and let you make a guess, but why don't you just do this in your minds and just think about, what would you guess is the probability that someone goes down to 1% and comes back? Is the probability more than 1%, less than 1%, more than 50%, less than 1 in a million? You know, what's the order of magnitude? What should this roughly be? And does it matter what the initial values are of the, you know, I sort of didn't give you that information. I just told you that they were all integers greater than 1, and that they add up to 100. You know, does that actually matter? Okay, so we'll answer that in due time. First of all, I'm going to develop some machinery. So what's a martingale? So if S is a probability space, x0, x1, x dot be a sequence of random quantities, aka random variables. And so informally, imagine you're acquiring information about S. Well, S represents sort of the set of all possible outcomes. You have a probability measure that assigns each possible outcome a number, a probability. And so you imagine that these are random quantities, they're random variables, and xj, if you like, represents a quantity that's known to us at the jth stage. Maybe it's, what is the probability that Kamala Harris will win, given everything we know up to stage j. Okay, now if z is any random variable, I can let the expectation of z given fn denote the conditional expectation of x, oh sorry, this should be z, I guess, scheduled expectation of z, given all the information available to us on the nth stage. And so I say the sequence x of n is a martingale if, well, first of all, the expectation of x is less than infinity for all n. But furthermore, the expectation of x plus 1 given everything you know at the nth stage is x sub n for all n. So informally, it says, taking into account all the information I have at stage n, and the expected value at stage n plus 1 is the value at stage n. Okay, so thinking of the Kamala Harris example, this means that if the price is 37 now, taking that into account, taking into account everything I know, the price today is 37. I expect that the price tomorrow will also be 37. Okay, this is often used in the stock market. So I have a good friend who's a hedge fund investor who used to tell me, or hedge fund manager who used to tell me that the best predictor for the price of a stock tomorrow is the price of a stock today. So given what you know today, roughly speaking, the expected value tomorrow is just the value today. Because if you knew it was drifting upward and you didn't, then you would price up the stock now. And assuming there's no information, no one with special information, that couldn't happen. Okay. So classic example, if x sub n is some known value, you can imagine x sub n plus 1 is x sub n plus or minus 1 with the things chosen by fair coin tosses. So at each stage, S goes up by 1 or down by 1. That could be what's happening with the price of the betting market contract with Kamala Harris. Okay. So now, what's the stopping time? So if t is a non-negative integer valued random variable, I think of t as giving the time at which the asset will be sold if the price sequence is x0, x1, x2, dot, dot, dot. And so I say that t is a stopping time if the event that t equals n depends only on the information available at time n. So in other words, the decision to sell at time n depends only on information, such as maybe asset prices or weather or anything like that, as I have at time n. It doesn't depend on any future unknowns. The optional stopping theorem is as follows. This is contained in many basic probability books. It basically says you can't make money in expectation by buying and selling an asset whose price is a martingale. So precisely, if you buy the asset at some time and then adopt any strategy at all for deciding when to sell, then the expected price at the time you sell is the price you originally paid. If the market price is a martingale, that means somehow you cannot make money in expectation by timing the market. So when I was a kid, my dad used to tell me about these investing books he would look at that would tell you, hey, here's a great strategy for making money on a stock. First, you find a stock that appears to be what we call a rolling stock, one which seems to go up and down and up and down and up and down, frequently covering the same trend. Then what you do is you buy low and you sell high. You buy low, you sell high. You buy low, you sell high. And you repeatedly do that, and gradually over the years, you just can't help but make money. As it goes up and down, you're gradually just making money as you go. It's much better than just buying it and holding it. Now, what my dad pointed out to me, even at the time, is that a lot of these people selling these books did make a lot of money, but they made their money by selling the books, not by their actual market trading. Because in fact, such a simplistic strategy is just, buy below a level, sell above a level, is not likely to be a moneymaker. In fact, if the market market is efficient and the prices are martingale, then no matter what you do, the expected price when you sell is going to be the original price. And if there are any transaction fees or losses in the individual trades themselves, you may end up losing money. Okay, so here's Dube's optional stopping theorem phrased more formally. If the sequence x0, x1, x2 dot dot is a bounded martingale, and t is a stopping time, then the expected value of x sub t is equal to x0. So think of x0 as maybe the value. You buy the stock for price x0, then it goes up and down. You adopt any strategy at all for deciding when to sell. And when you reach the time that you want to sell, you sell it. X sub t is the price you sell at. And this says the expected sale price is equal to x0. Okay, now I mentioned that these markets are not perfectly efficient. So, if you look at that market on the vice presidential candidate or on some of these early elections, sometimes you'll find that the probabilities add up to more than one. And when that happens, one thing you can do is just buy no on everybody. And it may be that if you buy no on everybody, you can make a little bit of money in expectation. Now, but what you find out is when you do that, it takes a certain amount of hassle, a certain amount of work, and you have to go through and place all the bets and time. And it may be that when you do this, you put in a fair amount of effort and you make $20 or $50 or something for a fair amount of work. And you may find that the amount of money that you're able to make, they have strict bounds on the amount you're allowed to put in the market, is not really that high. And so because of that, it should not surprise us that there are some inefficiencies in the market. So the way a finance person might think about this is that it's very unlikely to just see $1 million lying in the middle of the road with nobody picking it up. Or even just seeing a $100 bill in the middle of the sidewalk. You wouldn't expect to see that. If it were there for any length of time, somebody would pick it up. On the other hand, imagine you looked on the sidewalk and you saw a little coupon that says one free appetizer with the purchase of an entree at Denny's on Saturday. Okay. In principle, you could pick up this coupon, go to Denny's, find somebody who was already in the process of purchasing both an entree and an appetizer, offer to sell this coupon to them for a little bit less than the price of an appetizer, and you would make some free money. Okay, so this is an arbitrage opportunity where you have a chance to make a little bit of money. But obviously, the amount of effort required to undertake this thing, which may or may not be fully legal, far exceeds the value of the coupon itself. And so, you might say that perhaps the inefficiencies that you might find in predicted or some of these things, you might say, are these more like $1 million lying on the ground for free, or are they more like, the Denny's coupon, where, okay, it's there, but it's not really worth your trouble. Just for illustrative purposes, I have made some bets on these markets, and did make enough money with arbitrage opportunities to buy chocolates and pizzas for my class on some occasions. So, I've made several $100s doing this sort of thing. But, it takes some fiddling around. Would you say it's really worth it? I don't know. But I want to point out here is that the way I was able to make that little bit of money I did was by spotting inefficiencies, spotting places where asset prices could not all be martingales, or where, their prices didn't add up to one, something where it had to be inefficient. And so the optional arbitrage not only tells you what happens if you have an efficient market, but it also gives you some hints about how to make money off of inefficiency. And several years ago, I was a professor at NYU, an assistant professor there, and I was teaching something about martingales, and I realized that there wasn't really a good resource on the internet for the optional stopping theorem. So here's what I put up. I'll show you this. I put up this nice little note. It's about a page long or too long. It describes the optional stopping theorem, gives a couple examples, a few problems you can solve with this. And I kind of felt like I was fairly important at the time because in some sense, this article was sort of the essence of what makes trading in assets work. The efficient market hypothesis, it tells you what happens when the market's efficient. It also tells you how to make money if it's not efficient, and somehow the whole New York economy depended on this, and I was propping up the optional stopping theorem, that stopped propping up New York. So I looked out the window, I kind of felt like, yes, this is me here. And so I want to point out that a year or so from that, you'd had this nice optional stopping theorem online. Someone had made this beautiful Wikipedia article, but if you look down further, you'll notice even today, it still only has one external link, which is my little article, from 10 years ago. Okay, but that's, anyhow, the optional stopping theorem, and you can now read about this in all kinds of places. And so we want to see how that helps us in this example. So, all right. The theorem, how would you actually prove it? Well, you can prove it by induction. It's not that hard if the stopping time is bounded. So, let's say I tell you that the stopping time is bounded by 100. So you have to sell at one of the first 100 steps. Okay, so what I know by the definition of Martingale is that if I were going to wait until step 99 to sell, then once I reach step 99, the expected value at time 100 is equal to the value at 99. So I might as well just sell at time 99. If I reach to time 99, there's no advantage to waiting another day to sell. I may as well sell at day 99. Okay, but since I know I'm going to sell by day 99, I can now iterate that argument and say, okay, when I get to day 98, I know that if I reach 99, I'm going to sell then. So the expected value at day 99 is the value at 98. So I may as well sell at 98. And then you may as well sell at 97. You may as well sell at 96, and so forth. And finally, you conclude that you may as well sell at time 0. There's absolutely no advantage to waiting before you decide to sell. Okay, so that's what happens if t is bounded, and if t is unbounded, there's a certain limiting argument, but it's essentially the same story. So now, imagine that x sub 0 equals k is a positive integer. And for n equal to greater than 0, we have x sub n plus 1 is equal to x sub n plus or minus 1, with the signs chosen by fair coin tosses. So fix some c greater than k, and let t be the smallest time, little t, such that x sub t is equals to 0 or c. For example, maybe c is 100 and k is 37. I'm just going to keep tossing up and down until either I reach to 0 and Kamala Harris has not been chosen, or I reach 100 and she has. Okay, and so here's the claim. The probability that x sub t equals c is just k over c. It sort of makes some intuitive sense in the example I gave. If I start at 37, then the probability I reach 100 before reaching 0, it makes sense that it should be 37%. Okay, well, this is sort of telling us that that's actually true. And the proof, well, you could do this in various ways. You guys are all math contest people. I'm sure if this came up on a mock problem, all of you would very, very easily work this out in a dozen different ways. But let me show you how to do it using this optional stopping theorem. So the expectation of x sub t is equal to the probability x sub t equals c times c. It's just the definition of expectation. That's the probability xp equals 0 times 0, which is the probability xp equals c times c. Now, by the optional stopping theorem, the expectation of x sub t is equal to x sub 0, which is k. So you divide both expressions by c, you get the probability x sub t equals c is exactly this k over c. And that's the whole story. Okay. So now, how do we go from here to solving our problem? Well, okay. Before I move to the problem, let me tell you a little bit more about places in which the martingale arrives. So it turns out that if x is any random quantity, then the expectation of x given f0, expectation of x given f1, given f2, etc., this is a martingale. And so people, when they talk about what's the expected amount of money Moderna is going to make off of its COVID-19 vaccine. Okay. This is some number we don't know. But we can say, well, what's its expectation given what we know now? And maybe, you expect it to be, I don't know, some number of billions of dollars. And then as you get more information, that number goes up or down. If some tests come back well, if the competitors don't do as well, things like that, it might go up. Other things might make it go down. And you're gradually watching what's happening in the world. And every day you get a little more information, it goes up and down. And so It turns out that within a mathematically formal setting, if x is any random quantity, and you look at the conditional expectation of x given increasing amounts of information, so f sub n is the amount of information you know at stage n, this is always going to be a martingale. Okay, so here's a cute little example I'd like to show. So imagine that Ivan sees an email from his girlfriend with a subject line that says, "Some possibly serious news." And based on that, he thinks, so it's a rocky relationship time, he thinks there's a 20% chance she is going to break up with him before the email ends. Now, each time he reads a new line in the email, he revises his expectation, and his heart jumps or sinks. Okay, it's an emotional moment. And we've all been in situations like this. Maybe it's a relationship. Maybe we're seeing whether we got accepted to a program or how we did on our exams or whatever. But as it happens, each time we get a little bit more information, the emotions arise within us, and we revise mentally our best guess of what's going to happen. So starts, she says, "Oh, Ivan, I've missed you so much." Drops to 12. Sounds pretty good. "I have something crazy to tell you." Jumps to 24. Sounds a little ominous. "And so try to do this by email. Where's your phone?" Okay, jumps to 38. He's much more worried. "I've been spending a lot of time with a guy named Robert." Okay, who knows where that's going. "A visiting database consultant on my project." Okay, that sounds sort of platonic. 34. "Who seems very impressed by my work." Okay, clearly this is professional. "Robert wants me to join his startup in Palo Alto." Okay, this could be leading up to something exciting. "Of course, I said I'd have to talk to you first." Okay, that's encouraging, because you're absolutely a priority in my life. Very good. "And you'll be at MIT for at least 3 more years. But I'm just so confused on so many levels. Call me, I love you, Alice." Okay. And then we're at the end of the email, so he knows the breakup message has not happened. He's down to 0. Now, there's a certain philosophical point of view on the universe called, Bayesian statistics or Bayesian epistemology. If you look at Bayesian, you read all about this. And the basic idea is that we all have these mental probabilities for everything we don't know. And we gradually revise those probabilities as we gather new information. And according to our own estimate of what's going to happen in the future, these probabilities should be evolving as martingales. Okay, so at least according to their own probability measure we would put on the future trajectory of our own probabilities, we expect these things to be martingales, or we see these things as martingales. And so you should always think, where do martingales apply? They sort of are inside of you everywhere. Anytime you have an emotionally fraught situation where you're gaining information about something you care about, there's always a martingale inside of you. Okay, so now let's move on to the solution to this exam problem. So using the optional stopping theorem, we can argue that the probability the ith candidate wins before getting down to 1 is, well, what's it going to be? So remember, the ith candidate starts at some value, maybe 5, and then the candidate is either going to go down to 1 or is going to win. And so let's just ask, does the ith candidate win before getting down to 1? And the probability the ith candidate wins before getting down to 1, well, basically we have to just rescale the story from the previous picture. It's going from 1 to 99. But basically, if we subtracted 1 from that, it would be going to 0, or 1 to 100. Subtract 1 from that, it's going from 0 to 99. So P sub I minus 1 is going from 0 to 99. And the chance it gets to 99 first is just the initial value divided by 99. That's what we showed before. So this is the probability that the ith candidate wins without there being an epic comeback. Okay, that's the probability that some candidate does it. Well, you just add them up. This is probably the first candidate wins without an epic comeback. But 2 would be probably the second candidate wins without an epic comeback. Okay, these are disjoint events. So the probability of some of them occurs is the sum of all of them individually. If you add these up, you get 1 over 99 times the sum as I goes from 1 to 23. A piece of I have 0 minus 1. This is 100 minus 23 over 99. That's 77 over 99. That is 7/9. Hence, the probability that somebody makes an epic comeback before winning is 1 minus 7/9 or 2/9, about 22%. Based on this, you might think maybe epic comebacks are not so unusual after all. Now, this may seem a little surprising. I mean, obviously, this win for the Super Bowl is something that we're going to be talking about for decades here in New England. It's a great, proud moment. Way down so far, still managed to pull through. And certainly, if you were the candidate who went down to 1% and then rose miraculously up to 100%, you would feel you have a story to tell. You'd say, oh, I was there. Everyone had written me off. The other candidates were all higher, and somehow I sit there at 1%. And, the media, the news, they all said I couldn't make it. And lo and behold, I showed them wrong. And you tell your grandchildren and you brag about it for centuries. But in fact, at least in this particular story, it tells us that 2/9 of the time, whoever wins is going to be someone who made this epic comeback. So almost a quarter of the time, it'll be someone who went all the way down to 1% and had this miraculous breakthrough. Okay. Well, sort of the reason for that, if you really think about it, is that most of these candidates at the beginning probably don't start out that high. Given the numbers add up to 100, on average, they're, what does that mean, 4 or something? So they're not going to be that large on average. So, some of them will be smaller, and for the smaller ones, it's not so surprising that they might get down to 1 and still make it. But even still, when you first hear the story, it's not what you would guess.
Liang Xiao asks, are there any computer simulations for this?
Computer simulations? Yeah. Yeah, there are lots of computer simulations. I mean, let me, so if we just go back to, I look at something like Brownian motion, let's see, and look at images, you will find, well, okay, these are 2-dimensional, but here's a 1-dimensional version. So this is what we call a Brownian motion. This is a model for like the stock market, it's going up and down. But if you want to know how they actually generated this on a computer, most likely they, they didn't draw in every individual point. Well, there are a number of ways they could have done it, but one possible way is that they divided time into a whole bunch of very small increments, and in each one they tossed a coin to decide whether you went up 1 step or down 1 step. And you do that enough times, then over time the process starts to look like, and if you scale, basically after time n, what will happen is that the up or down fluctuation is on the order of square root of n. So if you scale by n one direction and horizontally and root n vertically, in the limit you get this continuum process, which is what we call Brownian motion. It's also sometimes called the Wiener process. And this is important because Norbert Wiener was a famous MIT professor for several decades. During the first half of the 20th century, we have a Norbert Wiener common room where we hold all our activities. We have a bust of Norbert Wiener sitting there. And actually, if you come to my office and visit me sometime, you'll see that I actually have Norbert Wiener's desk, the desk he used at MIT, with a little plaque on it sitting in my office. Okay, but this is the Brownian motion, and it would be kind of the best example of a simulation. And if we wanted to write a simulation on our own, I'm sure we could do it. Let me see if I could just do simple random walk simulation. That might give us a simple random walk simulation. Here's one. Yeah, this is exactly what I said. So we imagine this is somebody who's walking, but it's a very simple-minded individual where each step the person just tosses a coin to see whether to go 1 step up or 1 step down, or 1 step forward, 1 step back. And so this keeps track of the person's location as a function of time. So we have a few steps back, a few steps forward, back, forward, back, and so on. And this, exactly a simulation of the sort that I described. Okay, so it goes down, it goes up, it goes down, and this is a simple random walk. And so if you started this thing at 37 and you let it keep going up and down, at some point it would either reach 100 or 0, and then we'd be at the end. Okay, good. Thank you for that question. I also want to point out too that this thing about ever coming back not being usual would be different if it were a smaller example. If there were only 7 candidates, then you could use the same argument, and you find you would get a probability of 6 over 99, which would be 2 over 33. It would only be about 6%. And so, the fewer the candidates you have, the more unlikely it is for you to see one of these epic comebacks. Okay. Let's see. Oh, okay, so that's anyhow the main part of the presentation and story I wanted to tell you. So why don't I stop now and take questions? I'm allowed to do that. So if anyone wants me to riff about efficient markets or trading in derivatives or politics or relationships or any other crazy thing, or applications of these things in higher courses, just ask a question and I'll try to answer. And I'm actually going to switch back now. If I can, I'm going to try to stop sharing my screen. And if I can, I'm going to go back to where you can see me face to face. So let me see if I can make this work. So I go back here. Okay, so the question is, can you see me now?
Oh, yeah.
So I do not see myself. You may have to click on me somehow to blow me up. Is that how? So I have to.
Rohith Raghavan asks, how did you make money off of inefficient markets?
Well, first of all, the easiest way to think about it is imagine that you knew that Kamala Harris was going to win. You had insider information. You can just buy for 37 and sell for 100. In fact, you might wonder what is preventing Joe Biden himself from doing that. He could go put a bunch of money on the market, then select Kamala Harris, and then cash in. Okay, he's probably not going to do that because it would be tremendously embarrassing if it were ever found out, and the stakes are fairly low. You can't make a ton of money that way. So no one really thinks that it's likely that he is secretly making a few $100s off of bets like this. But in principle, he could. There's nothing physically stopping him. And so it's kind of always the case that if you have more information in the market, if you know what's going to happen and other people don't, you can make money. Now, the sort of inefficiencies I was talking about were even just on the course of one day, you know that the price tomorrow is going to be in expectation higher than the value of the day. You could buy today and then sell tomorrow and make money in expectation. Now, the sort of arbitrage I was talking about before would be something where maybe you don't even have to know, have any guess for the probabilities. It might not be a statistical arbitrage. It might be something like, maybe you find out that there are only 3 candidates and you know that one of them has to win. Maybe it's a place where it's impossible for one of them not to win. And what you could do then is suppose that their probabilities don't add up to 100. One costs 25, the other costs 25, and the third costs, say, 30. Okay, so you can buy all 3 of them for a combined 80 cents. So you spend 80 cents and you buy a contract on each one of them, and then at the end, one of them has to win, so you're going to get $1 back. So you invest 80 cents and then you win $1 no matter what. Okay, that's the sort of thing you could do in an efficient market. Okay, and if something similar were happening in in the stock market or derivatives, maybe many examples where you have some information, you have find some things that don't add up to where they're supposed to. You can buy something and then make money without taking any risk. And sometimes that's the technical term for arbitrage. It's an example to make a risk-free profit. Good. Any other questions?
Earlier, you mentioned something about like Bayesian probability. Could you give a quick explanation of what that is?
Yeah. Bayes was this. He's actually a minister. What was it? The 1700s or something. So but he came up with this idea of probability. And the first he said, okay, I have to define what probability means. And he said, I'm going to say, for me, probability means the sort of the value of a thing if an event occurs divided by the overall value of the thing. That's how we define probability. So, what's the probability that Kamala Harris is selected? Well, I say, if you had a contract that gives me a car, if she wins, then the price of that should be 0.37 times the price of a contract that gives me a car no matter what. Okay. So that was his thinking of what probability should mean. And then using this point of view, he kind of argued that a definition for a conditional probability, that somehow the expected value of A given B is just the expected value of AB divided by, the probability of A given B is the probability of A and B together divided by the probability of B. And so another way to think of that is if I want to know that the chance A happens, and then at some point I learned that B has happened, then I say, well, what fraction of the space, including B, was comprised by A? Is it a scenario where A occurred? Like all the scenarios where B occurs, and what fraction of them does A also occur? And so I take the probability of that intersection divided by the overall probability of B, and I declare that to be the conditional probability of A given that B has happened. Okay, probably some of you have seen this definition in AP Statistics of Probability or wherever. Now, the story from there is what he took this definition, and there's a little identity that he wrote, which is basically just what you get by manipulating this definition in some ways. But the important part is not the identity. The important point is really just the way of thinking. That you have this notion of conditional probability. That you started out by having some probability for A, then you discovered whether or not B occurred, and then based on that, you revised your guess for whether, you revised your estimate of the probability that B occurs. A simple example, let's say you roll a die, and a priori, I think it's equally likely to be 1, 2, 3, 4, 5, and 6. And I want to know the probability that it's a 6. And I start a priori thinking there's a 1 in 6 chance. But then I ask you, hey, tell me, is it even? And you say yes. Okay, so now I know the only even numbers are 2, 4, and 6. So I revise my probability estimate and say, okay, now I think there's a 1 in 3 chance. Okay, so pretty straightforward. And but the idea is that you can apply this simple reasoning in all kinds of settings. And it really, there's a whole kind of philosophical point of view that says that this is maybe the basis of science. So you might think that, when I ask, what's the probability that I don't know, that if I mix these two chemicals, I get an explosion or something like that. And you start out with some a priori probability, and then you start doing little experiments, sort of actually mixing them and updating your probability as you go. And each time you get more information, you revise your probability. Or if I say, what's the probability that this drug cures cancer? Well, I start out with an initial probability, and then I try the drug on a few people. And each time I see what happens, I revise my estimate over whether the drug is effective. Maybe if it's effective, it helps some people, but not everybody. And so I don't learn for sure just from watching a few people's histories, but I gradually get more information. Okay, and so somehow in statistics there are these two ways of thinking. There's like the frequentist and the Bayesian way of thinking it, and somehow the Bayesian is somehow more logical, and he says you have this a priori probability, and you always just update it as you go. But then this sort of frequentist point of view may say that no, probability actually represents, well, you have to, you start out with any a priori sense, you kind of gradually get it from the data, and you shouldn't actually, when you write papers, the frequentists say you shouldn't start your paper by writing, I began my life thinking there was a 1/3 chance this was true. Then I did the following calculations, and at the end of the day, I concluded there was a 99% chance it's true. So the frequentists would say that's a silly way to write a paper because the person reading the paper might not have the same a priori guess you did, and you sort of pull that 1/3 out of nowhere. It's not clear how it got started. You shouldn't do that. You should rather say something like compute what they would call a statistical significance and say, okay, here is the likelihood I would have seen an effect at least this large if the hypothesis were true. And it's a kind of convoluted language, but it's sort of the one that has become more popular, even though in some ways the Bayesian point of view is more logical. And so there's kind of a different, and basically this is sort of a philosophical point of view of what the epistemological foundation of science should be. And it's something that you would talk about in your philosophy classes at MIT or other places, not necessarily in math classes. In a math class, of course, you could just take these definitions. This is what we define conditional probability to be, and start doing computations and solving problems. So I think the problem-solving aspect is sort of different from the philosophical aspect. Maybe that was a longer answer than you wanted, but that's the story. I could take one or two more questions if there's any people want to. Okay, maybe other questions?
Okay, thank you so much for showing up and presenting your talk on Martingales and optimal solving. So
okay,
let's give Professor Sheffield a round of applause.
Okay, thanks. Have a great summer, everybody.
All right, thank you so much.
See you later.
All right.